it just occurred to me, maybe you don't believe me. So I just wanted to show you the mean plus 2 times the standard deviation would be 185. So that's 2 standard deviations. You know what? For fun, let's do 3. The mean plus 3 times standard deviation. There. So actually, it's actually past 3 standard deviations. This happens a lot if there's, how do I put this? So in particular, hospitals sometimes get reputations for being good with difficult births or whatever. Or it could just be a fluke. It's not very likely, but it could happen, right? Or, who knows, maybe they lied about the data. Maybe twins happen more often than 2%. I mean, all these are possibilities. And this idea right here, what could be happening, that's where we're going to head in chapters 10 and 11 and 12. Just a little precursor. So what could be going on if you're not getting what you think you should be getting? And the answer is it could be all sorts of things. All right, now the last little bit is just some discussion, so let's look it over. For each of the following graphs, n equals 15, for which graph does p equals 0.2, p equals 0.5, p equals 0.8? All right, well, the 0.5 one has to be here because the data is symmetric, right? Okay, up here, we have to figure out which one of these is 0.2 and which one's 0.8. But you want to think to yourself, okay, which one's more likely to have, right? If the probability of success is only 0.2, then are you going to have a lot of successes or only a few successes? Think about it. So the answer is this one's the 0.2 because most of the successes are clustered at the low end, which makes sense. When you only have a 0.2% chance, 0.2, i.e. 20% chance of success, then you're not going to get a lot of successes. Whereas over here, this has got to be the 0.8 because there are a lot of successes. For example, 25% of the time, you got 12 successes out of 15, just for example. 25% of the time. Where am I getting the 25% from? It's because it hits the 25% bar over here. We had 12 out of 15, right? It's 12 successes out of 15 trials. That just isn't going to happen with something that's rare, right? Or something that's got a low chance of happening. It's going to happen when you have a high chance, i.e. 80%. So 80% means it's left skewed. Did you catch that? This is left skewed. Right? That's what's causing the high level success over here, but very few successes on the low end. That's why you've got the tail over there. And then the right skewed is 20%. Oops. All right. And then, of course, symmetric would be the 50% because then it's equally likely, both sides, 50-50, right? And you're squashed right around 7.5, which is the middle way mark, right? The 7 and the 8. Now suppose that n equals 15, n equals 30, and n equals 70. And this is the 0.2 graph. This is the same graph as this one right up here, top right corner. But what I'm doing is I'm increasing the number of trials. So notice as n gets larger, look what happens. See that? That's a bell shape. That's symmetric. And that's what they put down here. For n times p times 1 minus p is greater than or equal to 10, the distribution will be approximately bell-shaped. And just as a warning, that is the foundation for a lot of things that we can do in chapters 8, 9, 10, and 11. You have to have n times p times 1 minus p greater than 10 for binomial, i.e. surveys, right? So like Obama's approval rating from Gallup poll, that kind of thing. So this is just an idea. I want you to notice that as n gets larger, it gets more bell-shaped. As n gets larger, the picture gets bell-shaped.